Well, good evening, everybody, and welcome to the Leeds Philosophical and Literary Society talk for July. My name's Eric Blair. I'm president of LPLS, and it's a terrific pleasure to welcome Professor Craig Jordan to LPLS tonight. Craig is somebody that we've been wanting to talk to us for a long time, and he's on a visit to the UK. As some of you may know, we did have this scheduled as a hybrid event, and it was going to be in person and streamed. But unfortunately, because of the weather conditions and the cancelling of the trains from London, Craig has got marooned in London. And so we've had to switch it to an all online event. But just to say that, I mean, one of the purposes of LPLS is to disseminate the arts and the sciences in Leeds and the environs of West Yorkshire. And I think actually we can think of nobody almost who could do this better than Craig, because he's both a very eminent scientist and a writer, and he's produced an autobiographical work, and so he's also familiar with science and the art of science. So it's a very great pleasure to welcome you, Craig. And I'm going to just hand over to Rachel to just give you a little bit more of an introduction.
Thank you, Eric. And after this, you'll be putting up the slides, no doubt. Yeah. So Craig spent time as a student in Leeds, and we were so looking forward to welcome you back here. So he did his BSc and PhD here, and then has had a very international career, mostly based in the USA, and bridging mainstream university life and specialist cancer research centres. He's won many prizes, has had much special recognition, has been involved in a great deal of teamwork and mentoring, and served on so many boards of various different kinds. And as well as duties within institutions, he's done a great many visiting lectures, as you can imagine. He's been publishing for nearly 50 years, and the list now runs to over 800 items, which is somewhat daunting. And one of the most recent is indeed this book, about which he's now going to tell us. So thank you very much indeed.
Okay. I think Craig, you're muted. I got to unmute you, I think.
Hello, can you hear me now?
Yes, that's much better now. Yes, yes.
So thank you very much for those kind words. Thank you for the invitation. The sadness is absolutely all mine. When I was living in Leeds, all I could think about was I going to get to London, because the points had all frozen during the winter. So you'd be marooned at the station and your day's trip down there, or 2 days trip, had gone into the bin. Never in a million years did I ever think I would be marooned in London because of melting railway lines. Not possible. So interesting living through this. I have dedicated my lecture specifically to Professor Alan Roberts. This is in my autobiography, and this is a picture of Alan Roberts, who was in senior administration at the University of Leeds, but he was also an individual who was in as a colonel in the British Army. So I had known Alan for most of my career, and Alan sadly passed away before Christmas, and his wife Margaret and 2 sons, I believe, are watching this today. So this is dedicated to Alan, my dear, dear friend. I also wanted to recognize two other people who are in Leeds, who I believe will be listening. Karen Allen, her name in my lab was Naylor, superb technician, absolutely excelled in her academic life at the University of Leeds, and very proud of her achievements. Graham Prestwich was an individual, another superb technical person as an undergraduate at the University of Leeds, who worked in my lab and then became a technician in my laboratory for the funding that I got from the Yorkshire Cancer Campaign, and also AstraZeneca, that really propelled all of our work forward at the University of Leeds. So this is dedicated also to these two excellent technical assistants. So if I could have the first slide, please. So there you go. It'll be just click on the slide.
Yes. I think I'm there now.
No, you've got to go back one, please.
Yeah.
Okay. So I thought I'd impart the knowledge of where I come from, metaphorically speaking. It's the MD Anderson Cancer Center in Houston that is probably the largest and most complex cancer center in the world. For most universities, their cancer centers are, as you see here, a building. This is the administrative offices that administers 28,000 people working in the laboratories in the Texas Medical Center. So it's a very, very large, complicated University of Texas state driven organization. What I'm going to do, if I could have the next slide, is take you all on a journey. And that journey really expands over the whole of my career. And I did my PhD, and then I was sent to the United States, where I had to get my BTA, my Bean to America, and then come back to Leeds and impart new knowledge to be able to invigorate the University of Leeds. And this we did. What was happening in the early 1970s when I got there was everything was really focused and dedicated towards using combination chemotherapy to cure cancer. It had been done for leukemia. It had been done, or soon to be done, for other blood-borne diseases, but nobody had been able to do it for a solid tumor. So ICI Pharmaceuticals, that was at Alderley Park in Cheshire, I'd had a relationship with that company. Arthur Walpole, in charge of the fertility control program, he basically gave me a solid contact at ICI Pharmaceuticals, and they said, well, we're going to send you to America to work with one of our colleagues who's gone to work over there at the Worcester Foundation in Massachusetts. And the Worcester Foundation in Massachusetts was basically the home of the oral contraceptive. I'd done my PhD on failed contraceptives, and it was appropriate that I looked at modern day contraceptives at the Worcester Foundation. So I went off to work with Michael Harper. I got there, he'd left, he'd gone to Switzerland. And I was with my new boss. He said, you can do anything you like, but you have to get some money. And I phoned up Arthur Walpole and said, I was told I could do anything I like. Why don't we turn ICI 4647-4, your compound that wasn't tamoxifen yet, into a breast cancer drug. We know the estrogen receptor is in some breast tumors, and these are the ones that respond to endocrine therapy. Tamoxifen is not on the market yet. But this now gave me an opportunity to do something that nobody's ever done before. Work on a drug with industry, help organize clinical trials and clinical contacts. So this is the two things that were possible. Laboratory principles for the treatment, as you see on the left of this slide, that required experiments to give a good reason to use the drug as a treatment for breast cancer, and then to go and do clinical validation in clinical trials. That took about 20 years. So I'm there in the 1970s, as I said previously, at the Worcester Foundation. So setting up experiments was very, very important. You had to have lab to clinical rationale for doing this. Laboratory principles for prevention. The word chemoprevention for breast cancer hadn't even been used at this point. It was science fiction to think you could prevent any cancer other than not smoking in the first place. So 1970s, there was prevention. So we're going to go forward in these two parallel universes to see how medicine was changed. Next slide, please. So here was the experiment. It wasn't published in 2014. This is from a review article I was asked to write, but it was one that was designed and conceived at the University of Leeds. And what I've got here, if you could point up the percent of rats with tumors axis, this axis here, yes, so this is the percent, so 100% of the animals can get tumors. Days after a compound along the bottom, that was days after DMBA. DMBA is the chemical carcinogen that in a certain strain of rats, all of the rats get tumors. So if you don't do anything, they all get tumors, and it's a bit of a mess. As you see in the blue and the red here, by 100, 150 days, all of the rats have tumors. If you give a short course in green down at the bottom, a short course, no, green here, short course just for 30 days, which was what the clinical trials were projected to do, you get the carcinogen to initiate it. So then you want to control it, but you only control it about 60%, as you see in the light green curve, exactly there. If you continuously treat these animals, 90% of these animals remain tumor-free. And when I was at the Worcester Foundation, everybody got very excited when I repeated this particular experiment. And they said, oh my God, you've cured cancer. And I said, this is the most ridiculous thing. It's obvious. These are tumors that are endocrine responsive. They have an estrogen receptor. Tamoxifen blocks the estrogen receptor. This is an experiment of the obvious, but nobody had done it. Nobody was interested because chemotherapy was going to cure cancer, not a silly failed contraceptive. Next slide, please. So this is where I come from. And when I first went to Wisconsin, they recruited me specifically on the basis of they'd invited me over and they said, give a talk about, why we should employ you. And I gave them, showed them that slide, and they said, okay, you've got a job. No questions asked. You have a plan. We'll see it in a minute. The chairman of the department, this in if you go down to the car park at the bottom of the slide, and on the right-hand side, move up to the 6-story building here, that's the one. This was the Wisconsin Comprehensive Cancer Center, and I was on the top floor eventually with Dr. Paul Carbone and the other members of the staff that I will show you in our next slide. Next slide, please. So you go to be attracted to be amongst some of the greats of a discipline, cancer research, and these were the greats, but they were all connected. Greats develop greats. So front bottom line on the left-hand side, this is Harold Rush. He is really the father of cancer research in the United States. He had the ear of presidents. He set up a McArthur Laboratory of Basic Research on cancer research and regretted really until the day of his own death that he had not spent more time doing translational research, because his daughter was unfortunately a victim of breast cancer, and he had no way of being able to treat her. She had chemotherapy and that failed. So he listened to what I was saying, and Craig Jordan had a plan. I didn't know he had lost his daughter to breast cancer, but these facts were critical. If you move over on the other seated gentleman on the right, this is Paul Carbone. He was head of the medicine branch of the National Cancer Institute. He'd won the American Nobel Prize, which was the Lasker Award, for his work on being able to cure leukemias. I showed his staff the slide I've shown you previously on completely preventing breast cancer in these animals with long-term tamoxifen therapy. He offered me a job based on that one slide, originally done at the University of Wisconsin, University of Leeds. And he did something that was extremely courageous. He declared in his cancer center that no woman would ever stop her tamoxifen if she had a diagnosis of diagnosis that required a mastectomy, and they would take indefinite tamoxifen treatment, and they wouldn't stop it. Tamoxifen wasn't even on the market at that particular time, so they had internal protocols to make that work. So Paul is a visionary, because that obviously saved lives. Back row, left to right, this is Gerald Mueller here in the blazer, and Jerry was an early pioneer in endocrine therapy of breast cancer, and he had a postdoc here in the gray jacket, Jack Gorski, who I knew all about Jack Gorski because in my PhD I'd learned all of the literature, and Jack Gorski did the first experiments to identify the estrogen receptor by a technique called sucrose gradient analysis. You could bind it with estradiol, and you could see it at an 8S, that's a Svedberg estrogen receptor. This child here in the blue blazer with the glasses, that's me. And on the right of me is Doug Tormey, who was Jerry Mueller's PhD student and Paul Carbone at the National Cancer Institute's right-hand man. So it's a very close-knit family in those days. Now there are hundreds, tens of hundreds of cancer research workers in America, but in those days it was just a handful. Next slide, please. So this is one of my tamoxifen teams. So they're a tamoxifen team because we're working specifically on tamoxifen. We are trying to decipher what to do with it, how to use it, and it's the people that you meet and who come to want to work in your laboratory. I'm going to point out on the front row, starting left to right, PhD student, next, PhD student, Next, me, a PhD student, go up one, PhD student. Back, the young man that back here, with the beard and the long hair, who I would also always think he looked very much like Jesus, and jokingly said that in the lab before now. He was another PhD student. The others were all technicians, except this gentleman here with the glasses behind my head. This was Dr. Eno. I had been invited by the Chinese government to go to China for a 3-month visit, and they wanted me to go around towns in China and educate them about what I was doing. And ICI, AstraZeneca, said, well, we will fund you to do that because we need you to find out specific information about the Chinese. We're very worried whether the Chinese are going to flood the market with tamoxifen and release it through Hong Kong. So what I found out was, no, they weren't. So they said, well, we'll pay for all of your trip to go to China, but you have to do something for us. We're going to organize a meeting at the New Otani Hotel in Tokyo, and we're going to get every breast cancer surgeon in Japan to come to your lecture, and that's what you have to do to you. No problem, I'll be there. Man behind was in the audience and was listening to my talk and said, I'm going to work with that man. He came to work with me, funded by himself, when I was at Wisconsin, and he sent another 10 people from South Korea and Japan to work in my laboratory. So we had an international aspect of the tamoxifen team. The important thing was every one of these people from the Far East became chairman of departments, and one became head of their cancer center. So we made a big impact worldwide. Next slide, please. So what did the clinical results showed when everybody caught up in 2005? Remember that slide I showed you was in really the data from the 1970s. So here on the left, it said recurrences. The recurrences, tamoxifen therapy for 5 years, fewer tumors in the light blue occur in those that get 5 years of tamoxifen compared with control that get a placebo above. On the right, published in the Lancet, these are the mortalities, the people who are left alive. So 500,000 women are alive because of tamoxifen, and this was in 2005. Now it's multi-millions because tamoxifen continues to be used around the world in generic forms. Next slide, please. So chemo prevention. This was a laboratory idea. This was a laboratory name, chemo prevention, that was used in the scientific community, but nobody was really thinking about doing it. This was, a bridge too far, if you like, to be able to select populations to be able to do it. So in 1985, then became the dilemma when we started thinking about what were we going to do to be able to get nationwide clinical trials. And in 1985, you had to be able to prove safety in women who had high risk, and there was a mathematical formula to create that. So if estrogen is good for women's health to protect from coronary heart disease and osteoporosis, so it's good for those two, preventing those diseases, and anti-estrogen could prevent breast cancer but harm health. Next slide, please. So this is the Wisconsin tamoxifen study. It was set up from experiments that we did in the laboratory and discovered by accident that tamoxifen not only did prevent breast cancer in the rat model that I showed, but it also, in the upper panel, it had an effect on rat bone. But this is actually women. So tamoxifen in the upper panel was found over a 2-year period to build bone, completely unanticipated. The estrogenic tickle of tamoxifen was actually sufficient to build the bone. Tamoxifen tickles to lower cholesterol, so it's protecting against coronary heart disease. So this was, you know, a completely unknown concept, which now we call selective estrogen receptor modulators. And there are 5 FDA drugs that are FDA approved from experiments that came from my laboratory. And this is how we followed on with tamoxifen to be able to change women's health. Next slide, please. Cholesterol was really dependent upon long-term therapy, as I showed you, of 2 years. But depending on what you started off with, it didn't make normal cholesterol better than normal. It just kept it at normal, whereas it started to lower at percent of baseline cholesterol if you had higher cholesterol. So it was good for the high cholesterol people, but it didn't do anything harmful to the low cholesterol people. Next slide, please. And here was one of the exciting aspects of doing research at the University of Wisconsin. You can ask questions because we have superb animal facilities, and these were the models at the moment, if you like. So each generation goes and improves models that can have human applications. What you see here in the cartoon in the middle is what are called an athymic mouse. It doesn't have a thymus and it has no fur on it, but it's immune deficient. So you can put in human tumors into this mouse and they will grow, if they are estrogen responsive, in response to a capsule of estrogen. On the left is an endometrial cancer called NK101 that's going to be implanted under the skin, and under the right is a breast carcinoma on the right-hand side called MCF7. And we're going to use estrogen to prove both grow with the estrogen. And we're going to see what happens with tamoxifen. Next slide, please. This is the breast carcinoma. And you can't see the breast carcinoma because tamoxifen has inhibited estrogen-induced tumor growth. On the other side of the mouse, on the left, the mouse is dragging a huge tumor around in the cage that is endometrial cancer that's growing with tamoxifen. So I started showing these, and I first released these data at a conference in Italy, and there was sort of some gasps from the audience, but no big kerfuffle. I asked lots of my clinical colleagues in the United Kingdom whether they'd ever seen any. No, never seen any, doesn't exist. This is just a silly mouse. It's not really relevant to what we see in the clinic. And I looked at the papers and they never reported that they didn't see any, that they hadn't actually checked, I don't believe. Then there was letters to the Lancet. We've just seen a presentation from Craig Jordan, and it was by a group from Scandinavia. And they said, we've gone back and had a look in our records, and we found several patients who have been taking tamoxifen that had endometrial cancer as he has projected. And they eventually came out with a very, very large, eloquent paper of different doses of tamoxifen, different lengths of time, being able to increase and decrease endometrial cancer. Next slide. And this is the slide. So control in a large clinical trial from this group in 1989. Remember, we published in 1988 in Cancer Research, but we talked about it in 1987. And this is the cumulative frequency in the axis on the left and years on the right. So a very long, very, very accurate study. So yellow is control. These postmenopausal women have had no tamoxifen. If they got 2 years of tamoxifen, they got in blue an estrogenic tickle in some of the tumors. But the 2 years, you see, is way back here at that point where the red dot is. But if you continue the tamoxifen for 5 years, the tumors continue to grow. They're supported and they're ready to break out from the uterus to put women's life in jeopardy. I'm pleased to say that because of the clinical data that was really triggered by the translational aspect of the animal data of endometrial cancer, lives were saved, which is the whole purpose of doing translational cancer research. Next slide, please. So let's talk about preventing breast cancer. This was a project that was really started off in the United Kingdom by Trevor Powles, then head of the breast cancer program at the Royal Marsden Hospital. But the major study done in the Journal of the National Cancer Institute really set up and reported in 1998 that had all of these patients that were going to be randomized to placebo or tamoxifen to have a look at preventing breast cancer. Next slide, please. These are high-risk women. On the left is my initial publication of what I've showed you previously, but now back from 1974 in the Journal of Steroid Biochemistry. In red, the animals aren't treated with tamoxifen, they're just treated with the DMBA. That mammary cancers come from the DMBA. And those that receive tamoxifen in blue, you pretty well wipe it out. So the experiment worked in animals, and gosh, those tumors that are ER positive, they have a dramatic decrease in breast cancer. The tamoxifen goes down dramatically. If the estrogen receptors are ER negative, they are fewer and they are not affected because there's no target, the estrogen receptor, in an ER negative tumor. But there are far more positive ER positive tumors in a women's breast cancer than ER negative. So that came some, 74, 84, 94. So that's basically 30 years later to do that translation and save women's lives. Next slide, please. Endometrial cancer in the tamoxifen prevention trial, which was set in motion. You can see the number of cancers on the left axis, and the total cancers here are with tamoxifen, and they're in the blue. And you can see there are basically nearly 3 times as many endometrial cancers in the tamoxifen group, but it's age related. It's age related, and it's only postmenopausal women who have the majority of tumors. In the premenopausal women, the control and the tamoxifen treated ones are almost the same. The reasoning being, it's obvious. These women still have menstrual cycles, and they are able every month to shed the cancer cells, because endometrial cancer is predominantly a disease of postmenopausal women. Next slide, please. So here was what we discovered. We were discovering about tamoxifen unique properties, that there was anti-estrogenic effects and estrogen effects. Tamoxifen was switching on and switching off different sites around a woman's postmenopausal body. So for example, on the left-hand side, the anti-estrogen inhibits second primary breast cancers. Women who have one breast cancer are at risk for getting a second breast cancer, and that decreases it by about 50%. Anti-estrogens inhibit the recurrence of breast cancer if they're ER positive. Tamoxifen has an estrogenic tickle on the left-hand side. It lowers circulating cholesterol. It doesn't produce a beneficial effect on a woman's health, but it does produce a beneficial effect with lumbar spine density, which is preventing fractures of the spine. Increase in endometrial cancer, thickness, and cancer on the right-hand side. So this is the benefit you can get from women's cancer, preventing breast cancer, treating breast cancer from a failed contraceptive. Unbelievable results for a drug never designed to do that particular thing, and went forward in clinical trials by ICI Pharmaceuticals, both in America and in the United Kingdom, but only for the treatment of late-stage disease. We were thinking ahead, what do we do with that to really prevent breast cancer and be able to choose the most benefit for women for a drug that is still with us today because of the benefits it will provide. Next slide, please. So I was asked, I received an award from the American Association for Cancer Research, and you see on the bottom, it says Lerner and Jordan. Leonard Lerner, on the bottom of the page, was the man who found the first non-steroidal anti-estrogens by just, going through the collections in a company in America, and decided to have a look at them and see what he could find. And what he found was that they were anti-estrogenic. So his discovery, obviously I couldn't make my discoveries with tamoxifen if he hadn't made his discoveries to get ICI to make tamoxifen in the first place. So this was published in 1990 in Cancer Research to celebrate our award. So I wrote at the end of this particular award, important clues have been garnered about the effects of tamoxifen on bones and lipids. So it is possible that derivatives could find targeted applications to retard osteoporosis and atherosclerosis. The ubiquitous applications of novel compounds to prevent diseases associated with the progressive changes after menopause may, as a side effect, significantly prevent breast cancer. Okay, fantasy island, but this was where the field went. Next slide, please. So why did I say could do the bone trick? We found by chance, and all of the young people who are in the audience should pay the most attention to this. It's what happens to you by accident. It's you spotting that accident has done something never before to be seen by anybody else. It's not something to be thrown in the bin. It's the unexpected, the unanticipated that could potentially save lives. So these are animal experiments we did. This was unanticipated, an experiment that I would never have done in a million years had somebody from the biochemistry department decided to come to me and said, we know you test various compounds, anti-estrogens, and we know that estrogen is good for treating osteoporosis. We're developing agents that we could use instead of estrogen, and we would like you to do an experiment. We'll let you buy the rats. I found out an appropriate model, and this required ovariectomized mature breeder rats to be treated for 4 months with either ovariectomy, that means to take the ovaries out, and this decreases bone density. We measured it by ash density. The next one up in the violet, estrogen alone does benefit to bone, as we know. RALOXIFENE did benefit to bone. RALOXIFENE is a failed breast cancer drug that the company decided it was not going to go on with because it had failed at all to produce any good positive effects in the treatment of metastatic breast cancer. So we said, gosh, you know, it's doing good effects in this. So they then ended up marketing that to make $1 billion a year out of RALOXIFENE, a failed breast cancer drug, based on these data. Estrogen plus RALOXIFENE is good as estrogen alone. The two tickles simultaneously made this a very good candidate. On the right, we've got tumors per animal, and you can see her control. You're getting nearly 4 tumors per animal. In blue, you're getting, with low dose RALOXIFENE, you're getting under 1, and even lower with high dose RALOXIFENE. Published both in the refereed literature, that then the company who had originally come out with this as a drug called KEOXIFENE, they said it's been modified. Well, the only way it was modified was that this drug was now called RALOXIFENE. So it didn't modify it chemically, they just changed the name and patented it. Next slide, please. So here's the proof of principle of the SERM concept of RALOXIFENE. And I was the chairman of the breast cancer committee that you see on the right, that I had a premier committee of 6 or 7 of my colleagues who were the world experts at being able to detect breast cancer in patients. And this was looking for detection because these women were all women who had were being treated for osteoporosis, to look at fractures, and that's on the left-hand side. So placebo, the number of fractures decreased with 60 milligrams of RALOXIFENE and better with 120 milligrams of RALOXIFENE. So benefit by lowering it by 50% or more for osteoporosis. So that's the good benefit. Breast cancer absolutely wiped out virtually breast cancer when given to prevent osteoporosis. Never been seen before. You're treating one disease and it has a benefit in another organ target site. So these drugs became known as selective estrogen receptor modulators. They had selective action in estrogen target tissues and could switch on sites around a woman's body up or down selectively. Next slide, please. So what progress was made in chemo prevention? So this is the, was all of this worth it? So what I did, and published this in the European Journal of Cancer, I found out how many prescriptions there were for RALOXIFENE after a 10-year period of it being on the market. And they were being treated for the treatment and prevention of osteoporosis. So this was 200,000 women. And they documented the number of breast cancers in this particular population. So click on the red dot. So standard of care at this point was two things: bisphosphonates that would have a 8,200 women getting breast cancer. So that was a treatment. So they're getting more breast cancer, but it brings it down to 8,200. Next slide. This is hormone replacement therapy, and that's 14,292. Not as good as bisphosphonates, and it actually causes some breast cancer, which is of great concern because estrogen, and it needs, if women have an intact uterus, it needs a progestin, a synthetic progestin, medroxyprogesterone acetate to be given at the same time to stop a woman getting endometrial cancer. That switches off the uterus. It stops it proliferating. But the bad news is it basically causes about 1,000 more breast cancers. So you're swapping one disease for another by giving them medroxyprogesterone acetate. Next slide. RALOXIFENE, based on all of the data from these prescriptions in the 2000s, only produced 2,800 breast cancers. This is a huge, huge benefit. So remember, this is being used to treat osteoporosis, not prevent breast cancer. So this is a remarkable twofer. Next slide, please. This is 11,492 fewer breast cancers. Looked in terms of the National Health Service over here. This is 11,492 women who are not going to need surgery, adjuvant therapy, and probably die. Totally different concept. Give them RALOXIFENE. It's available over here. Next slide, please. So let's just turn now to another man in this particular scene, Doug Wolf, identified here. And Doug made a discovery in the laboratory. Don't change the slide yet. One of the greatest mysteries in endocrine pharmacology was when a man, Sir Alexander Hadow, did some translational research in the 1940s. He found in women that they had fewer breast cancers if they were 5 years after menopause. They'd been starved for estrogen for 5 years, and then you hit them with this particular high-dose estrogen therapy. So we were doing experiments on the development of drug resistance to tamoxifen, because long-term tamoxifen was in, and we found some interesting experiments that we didn't know the results, but Doug did an experiment. I said, I want you to do an experiment of grow up Marco's tumors. This is Marco here at the front next to me here. So Marco's tumors, want them to grow up. He's Marco's left to go on to bigger and better things. And we want to see what the different growth factors are involved in tumors to grow with tamoxifen or not. So these are what is the real cause of tamoxifen resistance. What Marco had shown, that if animals were also treated with estrogen, they not only were dependent on tamoxifen, but estrogen would make them grow too. So we were going to grow some tumors up and treat them with estrogen. And these would grow, and we'd say all of the growth factors for tamoxifen or estrogen were the same or different, and then study those. Well, this is what Doug found. Next slide, please. 3 groups. As you see down at the bottom here, it says weeks. These tumors are grown up. If we could have the weeks on number 2 down at the bottom. Okay, they're all grown up together, and they're either going to be tamoxifen continued, tamoxifen renewed, as in the open circles, and tamoxifen removed and replaced by estradiol. So Marco had done experiments when you basically treated with the estrogen. It was just the same as tamoxifen. It was the closed circles. I didn't see Doug around on the 6th floor of Cancer Center for several months. When he saw me coming, he would lock himself in the toilet, run away, and had no intention of ever communicating with me again. He then came into my office and said, we have to write to the editor of cancer research and withdraw all Marco's papers. I've done this experiment twice, and what Marco found doesn't work. It's a disaster. And he explained it all to me and showed me this graph. And I said, it's not a disaster, it's a discovery. So the lesson here is you've got to know the history of where your discipline comes from, because the PhD students and postdocs don't. You've lived it. So you've got to have transferred that along. So the one with the closed squares are the tumors disappearing. And what Doug had found is that instead of being a stimulator of growth, they killed the tumor cells. And I said, Sir Alexander Haddow is talking to us. And he was telling us that this is a model of why estrogen killed breast cancer in women for the 30 years before tamoxifen was invented and took over. It had been a complete mystery to everybody why that happened, and now we could find out. Next slide, please. So Haddow, during my PhD at Leeds was between 69 and 72 on failed contraceptives, but I learned everything about the field. And I read David Karnofsky's memorial lecture, and this was in cancer in 1970, after the first year of my PhD, and it was thoughts on chemical therapy. I could only have thoughts on chemical therapy because I had no idea of what was going on with chemical therapy, as there was no really molecular biology, and it was early days for any of that happening. So I read this, and he basically lamented the fact that some patients had tumors, it just disappeared when estrogen was given to the patients. And he said that the great disappointment is that nobody knows why this happens. But as soon as tamoxifen came along in the early 1970s, nobody cared at all. Next slide, please. I was honored to have the 38th David Karnofsky lecture, and I entitled mine Paradoxical Actions of Estrogen in Breast Cancer, Survival of Death. This is the medical oncology community in the United States. This is their highest award. I'm not a medical oncologist, but obviously they had a committee that thought this was appropriate. Just tell you a little side story. The chairman of the committee contacted me while I was in England, and he said, I need an answer for this question I'm going to ask you, either yes or no about the Karnofsky lecture. And if we were to offer you the Karnofsky lecture, will you accept it? And I said, but I don't think I'm eligible. I'm a PhD. No PhD has ever won this. And you're telling me I've won it. I mean, is this against the rules? You know, blah, 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 blah. Is this a yes or a no? Said the chairman of the committee. I said, yes. So I gave the lecture, The Paradoxical Actions of Estrogen in Breast Cancer, Survival and Death. We then had gone forward and absolutely understood with a series of dozens of publications exactly how estrogen kills cancer cells and estrogen blocks cancer cells growth. So the whole thing is a wonderful understanding of the molecular biology of a natural agent, estrogen. Next slide, please. So this is rather a poor slide. I'm going to have to put on my glasses, but forgive me. In the, I think it's the purple and the green in the middle, these are the controls of 2 experiments. And the 2 experiments are, number 1 experiment is that estrogen alone is given to the women who you see in purple underneath the green one. It's gray blue then, yes. And this caused an enormous gasping of breath in the United States when these data were published, because estrogen's not supposed to kill cancer cells. Estrogen's evil, it causes cancer cells to grow. So, and we say, and we have no idea what this is all about. And I said, excuse me, I know, just be quiet, Dr. Jordan, this is serious stuff. You know, we're clinicians here. And no, absolutely not. Before tamoxifen arrived, estrogen was killing cancer cells. This is an understanding of this particular paradox. What you see here in the light blue up at the top, this is estrogen and what is called MPA, medroxyprogesterone acetate. Medroxyprogesterone acetate is a progestin that has to be given to postmenopausal women. And these postmenopausal women now don't get endometrial cancer. We went through that because of the progesterone or progestin actions. So what we have here, everybody just scratched their head and said, we have no idea why the estrogen is. And I'm at the back of the room saying, I do. It's all to do with estrogen deprivation. Estrogen in this model that has been set up, they are estrogen deprived for 5 years or more, because Bernadine Haley, as the head of the National Cancer Institute, wanted it pushed as far away from menopause as possible. She was a cardiologist. She wanted to see whether women given hormone replacement therapy had protection from coronary heart disease. But that's not the model. Women take hormone replacement therapy as soon as they get near to menopause. They don't wait for 5 years and start giving it. So it's a bad experimental design, but it gave us good data that these women had a decrease of breast cancer, which was like my laboratory models, starved for 5 years. The one where the red dot is at the moment, this is estrogen plus medroxyprogesterone acetate. And everybody just accepted that estrogen and progestin caused an increase in breast cancer because that's what hormones do. I said, no, it's not. What medroxyprogesterone acetate, because what I'd been taught at Leeds is not a pure progestin. It has also glucocorticoid activity. It will block the glucocorticoid receptor. Now, the glucocorticoid receptor is in breast cancers too. And what basically happens, because of the pharmaceutical chemistry I was taught at the University of Leeds, I realized that this particular agent, medroxyprogesterone acetate, has glucocorticoid activity, and it blocks the effects of the actions inside the tumor. So instead of causing the tumors to decrease in size, it blocks the ability of the tumors to decrease in size, but it causes them to grow, so that you have really now reversed the effects of the beneficial effects of the estrogen by putting a synthetic progestin in that entirely. So this whole journal's written about this now, and I'm delighted to have contributed those special journal articles with one of my students, Dr. Abdulrahman, who is a Leeds graduate and qualified during her pandemic, so that is remarkable service to getting her PhD from Leeds. Next slide, please. So recognition of SERM action. The consequences of us recognizing it in estrogen, selective estrogen receptor modulation action in men and women. The same has been used for androgen receptors, progesterone receptors in this list, down in the list in the under future applications, thyroid receptor modulators, glucocorticoid receptor modulators, and PPAR gamma inhibitor receptor modulators. So this has been thoroughly investigated. Had I been doing progesterone receptor work, would have never discovered it, because what we found out is the estrogen receptor is the only one of the receptor subfamily of all of these steroid hormone receptors where we could have made the discovery. So some divine hand is actually guiding all of the work we're doing. We just have to be able to recognize it. Next slide, please. So let me just end with my dozen scientific survival suggestions. So this book is my autobiographical journey through my life, and it's the scientific survival suggestions are from the experience of the good, bad, and the ugly of my life. And I've met a lot of ugly, usually mentally deranged bosses who get a little upset and start not helping you, but trying to hinder you. I wanted to make this come out of Leeds University, and these are both of the iconic sites, the Parkinson Building Tower, and also the tower on the right that's part of the Great Hall. This is me as a child at Wisconsin, top left-hand side, and I love butterflies, so I had to have a butterfly. So each of my books on tamoxifen and other derivatives all have a butterfly on the cover. Next slide, please. So the scientific survival session. Carefully decide on your mentor or supervisor for your doctorate thesis or fellowship. Choosing a PhD supervisor is critical. Be cautious of the faculty member who tells you their plan for you to finish in a couple of years. No project is what it seems on paper. Mine was not at the University of Leeds. My supervisor, the late Ted Clark, wrote up MRC grants. He got multiple tens of thousands of pounds worth of equipment sponsored by the Medical Research Council or the Yorkshire Cancer Campaign, all of which turned out to be not possible to be done, even though I had the equipment. And it took 30 years for other scientists to do my PhD. So it wasn't happening in the basement of the old medical school by somebody who didn't know anything about what the future of molecular biology was going to be, because it wasn't a word at that time. Next slide. Train your time yourself to ascend in science. Your personality, dedication, achievements, and experience will determine whether you have trained yourself to be ready and are talent spotted. I had the opportunity when I went to the Worcester Foundation on leave of absence for 2 years from the University of Leeds to be sitting down with the greats in cancer research and in endocrinology. I was having dinner with, as the only person who knew anything about the estrogen receptor, but the people who discovered it. This was the people I could impress over dinner, and these people helped my lives with letters of recommendation because of what they knew of me throughout my early career. New environments and challenges provide invaluable experience to apply to the next stage of your career development. One story at the University of Wisconsin. A faculty member left, and I was then called into Paul Carbone's office, and he said, "Craig, you've done international quality control on estrogen receptors throughout the world with the Ludwig Institute for Cancer Research. You quality controlled it. You did all experiments at the university, no, not the university, the Worcester Foundation. But then the person in charge of the estrogen receptor suddenly decided to leave. And I said, then Paul Carbone calls me into his office and said, Craig, I want you starting Monday morning to take over the estrogen receptor for the whole of southern Wisconsin. I think you can fit England in the whole of southern Wisconsin. These assays come to us in the cancer center, and we want you to quality control all of the assays. You inherit all of his staff on Monday morning, go for it. So I called up my friend and colleague in San Antonio, Bill McGuire, and he said, I don't know what the problem is. It's an opportunity. You have to understand, you have the training. You just need the courage to be able to do this. So over the weekend, my laboratory went from 10 to 20 people and twice the space in the cancer center. It was a huge undertaking, but I took it all very seriously and didn't really give the responsibility to anybody else for me to sign all of the forms for the patients in southern Wisconsin. Next slide. Know the literature of your chosen topic. Who did what? When I was at Leeds, I was doing fairly mundane experiments, but what I was doing is learning the literature and memorizing it, so if I ever met the person, I would know what they did. So know everything about your chosen topic. Become an expert in your small area and learn all of the literature written by those who came before you. So you can spot things out. I spotted the Haddow thing. I suddenly was going out to dinner with famous people like Elwood Jensen, members of the National Academy of Sciences. Another person, which was on that slide, Jack Gorski. My PhD that didn't work was based on Jack Gorski being able to identify the estrogen receptor on a thing called sucrose gradient analysis. So memorize it. If you've got a good brain, you can come up to an answer, and you can answer any question anybody throws at you because you have got really all of the information in your brain. You don't have to go and look on your computer like a half-wit. Thank you very much. Next slide. Ensure your director or chair has an agenda and you are in it. Paul Carbone had an agenda for me. I went from assistant professor to tenured full professor in charge of the estrogen receptor laboratory, and in a remarkable 6 or 7 years. What basically then went, he had an agenda for me. he got me a job when he decided to leave the University of Wisconsin. He proposed me to go to Northwestern University to the Lurie Cancer Center that was just setting up. And he told the individual in charge, Steve Rosen, who was having his first director's job, hire Craig Jordan. You know, he's a good chap. And so I went down there and I suddenly found the ability to be able to explain what I was doing to donor groups. And I accumulated a huge clientele of donor groups. Those donor groups gave me $1 million a year for the next 12 years. Another donor group gave me another $2 million a year for six years. I got the top collaborative research grant that you can get in America called the SPORE grant. There were only 8 in the country, and I got one without an established cancer center in that. And we also had another grant of clinical research that was done in our cancer center. So this became a huge boost to my career. And my cancer center director, Steve Rosen, he then made sure I got lots and lots of opportunities. And by sheer coincidence, if any of you out there can get hold of the cancer letter that's available in, it's the ASCO Post. The ASCO Post have just had Steve Rosen interview me about our time together and all of the things that really changed medicine that came out of this huge investment of money in his cancer center. So the ASCO Post is available. It's going to be available in the next few weeks as an online version as the interview, but also as a print version. There are the bad people, and I've had 2 experiences, and in my autobiography, I don't name names, so they're not in there for litigious reasons, obviously. But they become very upset that they're younger than you. Actually, you're younger than them, but that you've done more than they have. And money becomes an issue. If people ended up giving me money, they wanted the money, but it wasn't given to the cancer center for them. It was given for me to do the things in my research. So you have to watch out that you are going on board with a director who has your best interests at heart, as in the book Steve Rosen, and not others unnamed in the book who have only their own interest. And one of them got fired very, very quickly. Next slide. Number 5, get documentation that says what you have achieved. This comes from my grammar school in Cheshire, where by the time we got up to the 3rd form, after our 11+, we were really being trained by our teachers how to conduct our careers for the next 40, 50 years. And what all of the teachers told us, it tells the story of what you did and what you will do in the future. It gives you an idea what you can do. And you also have this other dilemma, is that the documentation is not what you say blowing your own trumpet. It's written down. If it's not written down, maybe it's untrue. Maybe you fabricated it. So it has to be written down by a 3rd party. If you're in the Royal Society, you're in the Royal Society. In my case, you're in the National Academy of Sciences, you're in the National Academy of Sciences. These are secret organizations who promote their own membership, and you never really know what the system is. The more professional awards you receive, these reflect the opinions of your professional colleagues about the value of your professional contributions to medical sciences. So that's the most important thing. not blowing your own trumpet, but the people are blowing the trumpet for you. Next slide, please. Experiments are conversation with nature. We've seen that. The conversation with nature, like Doug Wolf's experiment with estrogen killing cancer sign. You define a question, and based on the selection of an appropriate model to answer your question in humans, you isolate the parameters of interest in a single variable with appropriate controls. The controls are critical to prove you can do what others before you have done. Those controls don't come out with that answer, you've done the experiment wrong. If the answer to your question does not give you what you anticipate, then your premise may be wrong, but only if all of the controls are perfect. Nature doesn't lie. It's telling you something different if the controls are right. The idea you have is incorrect. So those are the results you've got to pay attention to. Drug killing cancer cells instead of making them grow with estrogen. Pay attention to that sort of result. And that's what we did. And we've solved a lot of problems in medicine. Next slide, please. Number 7, follow your instincts about what you want to achieve. Have a goal. I only wanted to participate in developing medicines to help people. That is pharmacology. That's what I wanted to do. Eat, sleep, and work at your passion. I mean, it's your passion. You've got to use 7 days a week working on it, preparing papers, preparing presentations. It's a privilege to participate. It's not your right. It's a privilege. So you have to earn that right with publishing things that people will fund and train graduate students that will get careers of their own because you've trained them correctly. Next slide. Now an opportunity when you are presented with change. Opportunities occur rarely, but when they occur, you must seize them with alacrity. It is the only way forward. I was suddenly made over the weekend to be head of the estrogen receptor laboratory. It was an opportunity. You didn't run away from it. So I'd phoned up this colleague in San Antonio, and he told me that this is an opportunity. Do not back away from it and void opportunities. These will occur rarely. So Bill McGuire, adage number 1 is an opportunity. Next slide. Give opportunities to allow your team members to excel. Give opportunities without self-interest. You must ensure a team member leaves better than when they joined. This means that not only your graduate students and postdoctoral fellows, but also your technical staff. Karen and hopefully Graham both started off their careers that have been very, very successful based on being technical staff, but they got their name on publications. They could show this work that I did had merit to get published in refereed journals. So that is a big boost. Their inclusion on publications is essential to enhance their career prospects. That is the important thing. Not yours, it's their career prospects. And it worked for Graham and Karen. Next slide, please. Number 10, understand it's your responsibility to obtain support for your science. Ehrlich gave us one more lesson of science that is true today as it was in 1890, the 4 Gs. Glück, Geduld, Geschick, and Geld. Medical science requires Glück, luck. Remember, I had luck, but have patience, Geduld, because that's critical. You don't just go in over the weekend and cure cancer. You build building blocks, and it's like a jigsaw. You put all of this together so you see the picture. This is your picture and your career and your contribution. Each young scientist must become expert at selling the project by writing grants advocating opportunities to philanthropic organizations in the pharmaceutical industry. Graham and Karen were lucky enough to see my interactions with the then ICI pharmaceuticals. We would go every, we'll call it 6 months, for the time that the money they gave us. The clinical person whose budget was we were doing this, he gave us money out of his clinical grant to pay for rats from ICI to be sent every week to Leeds University for us to do any experiment that we wanted to do. If you go to the publications for VC Jordan in the 1970s, these are all based on ICI rats and the skill of Karen and Graham. Next slide, please. Science can be distracting, but publish or perish. Absolutely. Some scientists only see experiments as the goal, and their attention keeps wandering from experiment to experiment. I myself, when I was at the Worcester Foundation, I was interviewed by a very scary man at the Worcester Foundation who said, I've been asked to interview you about staying in America, not going back to Leeds. And I've got your CV, but you've not published anything. We've seen you working with clinicians at the hospital. We've seen you working with other postdocs. We've seen you with working with other universities. You haven't, what are you doing? I said, but I haven't discovered anything yet. So he looked at me over his half-moon glasses very angrily and said, tell them the story so far. That's what a publication is, telling them the story so far. The results in an appropriate refereed journal will piece together like a jigsaw puzzle, and it basically is as though you've never done the experiment, that it's worthless. But it may not be your experiments that are valuable for you. You may spark off what somebody else has done in the literature. So it has to get out there and show you have that expertise. Only refereed papers are relevant for jobs, promotion, and grants. People get dozens and dozens of abstract reprints of one, small piece on a piece of paper. Nobody cares. If it's not published in a refereed journal, it never existed. Don't waste your time putting on your CV 50 things you presented at meetings. It's a waste of time and you'll never get a job that way. Next slide, please. Last one. So when you publish, your colleagues and competitors will often ignore your landmark work. I mean, this certainly, many clinicians in the United Kingdom got very upset that I was telling them how they should be treating cancer because that wasn't my job description in England. Different thing with Paul Carbone, changed his cancer center for what I was saying. So your colleagues and competitors will often ignore your landmark work. Can you click it once, please? So they'll say, not practical, it won't work. These are encouraging words of wisdom from your senior colleagues. Click again. Even if it does work, it's not relevant. That's a hard argument to beat before you actually get going. But they're wearing down your resolve to go on and might give up. So they're winning at this point. Next one. Okay, it works, but not important. That's a really hard one because it takes 20 or 30 years, as you've seen with our tamoxifen work, to be able to get any traction for saving people's lives. So you've got to be in it for the long haul. Last one. Fantastic, you've cured cancer. I thought of it first. And they'll steal it. Happens every day. Final slide. So, Mr. Chairman, how would you like to proceed now?
Craig, thank you very much. We've worked through the slides, and shall we just stop sharing the screen? And we'll, I think we can probably take a few questions, and Kirsten's going to help me with the questions here as well. So you can write questions in the chat, or you can now unmute yourself and ask Craig a question. So
having said that, Eric, can I dive straight in with a question?
Yeah, sure. Yeah.
And I won't lend you any money, okay? Because I know I'm not going to see you yet. You'll disappear into the undergrowth.
Oh, thanks for your talk there, Craig. I've got to say, I found that whole idea of tamoxifen, having started life as a failed contraceptive, really reassuring. So I'm always trying to teach my kids, don't be frightened of failure. It's instructive. You know, we fall flat on our faces to learn how to pick ourselves up again. So I think that's great that we've got a biochemical example of that. My question was, last month, the University of Leeds opened this brand new building, the Bragg building, in honor of physicist Sir William Bragg, who with his son Lawrence were jointly awarded the 1915 Nobel Prize.
The First World War.
Yeah, for the discovery of X-ray crystallography. Yeah, and what I think 28 Nobel Prizes have been won since using X-ray crystallography. You know, it's unraveled the structure of DNA, insulin, penicillin. Now, am I right in thinking?
Went into the wrong business.
Did you use X-ray crystallography in your time when you were at Leeds to look at the structure of the 4674, the ICI compound, when it was binding the estrogen receptor? So I guess my question is, can we add tamoxifen to that list? Insulin, DNA, penicillin.
Okay, so here's how it went. So my PhD supervisor had this brilliant idea that we were going to, Valerie's now come on the screen. So I've lost you. So I'll speak to you because you're right there. Can you see me?
Yeah, we can all see you.
Okay.
Yeah.
So what basically happened was that my PhD supervisor said, okay, we've got a whole variety of anti-estrogens, but we also have the Asbury Department of Biophysics. And what we're going to do, because of all of their expertise in X-ray crystallography, is Craig is going to purify the estrogen receptor and then bind the estrogen receptor with estradiol, and he's going to bind it with a failed contraceptive, you know, we'll say anything, and crystallize them, go to the Asbury and do the X-ray crystallography, really boring. Nobody's interested whatsoever with failed contraceptives, but at least we'll know what it looks like, an estrogen and an anti-estrogen, to be able to look at things further. Two problems with that. First problem was I had to discover, and I did that about 6 or 7 years later than my PhD, had been to America, come back, had all this relationship with ICI Pharmaceuticals, and I said, very interesting, there's some strange pharmacology, so you've got to think laterally, strange pharmacology of tamoxifen. It's an estrogen in the mouse, but it's an anti-estrogen in the rat. So what we want to look at is whether there's a metabolic difference of tamoxifen in the mouse and in the rat. Does it tickle the uterus to make it grow in the mouse? And does it not do that in the rat? So ICI gave me the metabolites. And so the interesting story about this is that I have a look at 4-hydroxytamoxifen and a bisphenolic compound, 3,4-dihydroxy, and really look in mice and rats, and there's really no difference between the metabolites in mice, rats, and it's not really different than tomato. So it's not a species difference, okay? So then we make a discovery, and it's one of my PhD students, Clive Dix, my first PhD student, who was on an ICI scholarship, and who his claim to fame was he was the chairman of the coronavirus committee for the Prime Minister. So he did well for himself. I'm sure he's fingers crossed getting some nice honor, but it may not happen with the absentee Prime Minister. So the difficulty with trying to tease this out, we suddenly find Clive came and showed me results. And he said, you may have a look at the estrogen receptor with 4-hydroxytamoxifen. We called it monohydroxytamoxifen at that time. And what happens? These are the results I get. So he shows me the results, and tamoxifen is about 100th to 200th the affinity for the estrogen receptor. If you say estradiol knocks off radio-labeled estradiol, so it's apart, obviously. So he shows me this information, and I say, when I see that 4-hydroxytamoxifen and 3,4-dihydroxytamoxifen are the same as estradiol, Clive, do you know how to make serial dilutions? Go away and do it again. This is the most stupid thing I've ever seen. No anti-estrogen known to humankind has the same affinity as estradiol. What the theory is at the moment is that what happens is that the pure anti-estrogens, the anti-estrogens fall off the receptor, and that's why they're called anti-estrogens, because they can't stay on there to block the effect of estrogen long enough. Go away. Comes back, said, oh, okay, done the game, saying the right things. So this is how supervisors can be stupid but cautious, okay? We had discovered the first 4-hydroxytamoxifen as the first high-affinity anti-estrogen. Nobody ever seen such a thing before. So it wasn't in the literature because we had the literature. Panic at ICR, utter panic, because they were synthesizing compounds, and suddenly they were confronted with a compound that hadn't been published, patented. They'd given them to Craig Jordan, but nobody expected tamoxifen to succeed. Therefore, they'd never patented any of the metabolites because it was going to tank at any moment. They'd make a few £1,000s a year in England out of tamoxifen if they treated every breast cancer patient, because it was so expensive. So that occurred, and Clive came back and said, no, this is the answer. We discovered the first high affinity anti-estrogen, and this was the first of everybody else now synthesized high affinity anti-estrogens. Karen Naylor, who's appeared top right-hand corner, she knew I was going to mention her name. So Karen did experiments on 4-hydroxytamoxifen because we were interested in comparing and contrasting metabolic activation of tamoxifen, and we synthesized some compounds that have been blocked for metabolic activation, and these got published. On your right-hand side is Graham Prestwich, the other person by laugh at Leeds, and Graham was well aware about all of these anti-estrogens, and we had the first radio-labeled tamoxifen, and then 4-hydroxytamoxifen, and then all hell broke loose, and we weren't allowed to publish any of our data, and all very embarrassing for ICI because they had to admit that they had not worked this out. So going to America, me PRing tamoxifen to all the clinical trials groups, and everybody standing up and saying, this is the way to go, Craig Jordan's right, which would never happen, Craig Jordan's right, out of anybody's lips from over here. That was the problem for the clinical community. But over in America, you were in a team. And that team paid attention to the scientific work that came out of the laboratory that was there to help patients. It didn't matter that you weren't an MD. So that's really where the story went. And Graham did lots of experiments with radio-labeled antiestrogens.
Absolutely fascinating.
Thank you.
I think we'll just hold on to Kirsten, because I think we, it actually has been absolutely fascinating hearing all about your life and your science. And, you know, we could listen to you for hours more, but we have, I think what we will do.
Don't worry, just keep the Zoom on.
You know, yes. So that's what I'm going to suggest. I think, Kirsten, could you just kind of give us a vote of thanks, and we'll after that we'll terminate the recording, and people can be
terminated.
Terminated. People are free to stay on or log off or whatever. So Kirsten, over to you.
Can you two stay on?
Yes.
Oh yeah.
Yes.
Over here.
Yeah. We'll be here for ages. Don't worry. So thank you, Kirsten.
Yeah, gladly. Yeah, well, I'll just reiterate. Thanks once again, Greg. You mentioned the X-ray work that was done in the Asprey Centre. February 1945, end of the Second World War's in sight. And William Asprey had this grand vision for Leeds. He wanted to establish Leeds as this big national centre for blazing the trail in the new science of molecular biology and X-ray crystallography of biomolecules. And so he wrote to the Vice-Chancellor with this call to arms. He said, Leeds should be bold and help to lead the way. And things didn't quite work out for Asprey at the time, like he wanted to. But I think we can safely say that through the work you've done, you've realised his vision. Thanks to the work you've done, Leeds certainly has been bold and helped to lead the way. And the only thing about tonight was, I just wish there'd been more time for you to talk about your really interesting other double life. I am absolutely amazed that you've managed to do everything you have and have your military career as well, which I was really entertained to read in a piece you sent me that you described yourself as the Indiana Jones of medicine.
People talk to me the Indiana Jones of medicine.
Reading some of your adventures, particularly a story that you told about having to smuggle vaccines behind the Iron Curtain, I thought you probably more accurately the James Bond of medicine. Daniel Craig's given the job up, Craig, so you know there's a slot vacant there. Anyway, I've gone on enough.
Maybe the same age.
I'll just say thanks on behalf of Leeds Lit. Thanks very much. Thanks very much.
My pleasure.
And thanks to everyone for tuning in tonight. Okay, and you know, stay safe in the heat, stay cool, and we'll see you all next time. And enjoy the England game if you're going to go and watch it. Go Lionesses.
Okay. Thank you, everybody. Look forward to meeting you all again. All the best. Bye-bye.
My pleasure.